All right, class, we're going to get started. So before we go into today's lecture is going to be from lecture notes 13 on nonlinear regression. Right, so we talked about linear regression a few classes ago. Today we're going to talk about nonlinear regression. I just wanted to give a few clarifying points on the material for quiz 4. And just remember, I sent out a notice about quiz 6 was going to be held originally the day before Thanksgiving. I moved that one. So I sent an announcement on campus about the date for quiz 6. But quiz 4 is going to be next Monday in this room. And it's going to cover lecture material just through lecture 11, which was the last lecture prior to fall break. So the material from today and the material from Monday is not going to be on this quiz 4. So you'll have to go back and review some of that material. But really, we're just going through lecture 11. Just another note on quiz 4 is that I'm going to be including some true-false questions, which we haven't seen on previous quizzes. There have been some kind of yes, no, does this make sense or not questions, but you'll see some true-false questions. Where in the box, I'm really just looking for you to say true or false, right? So your final answer is just true or false. But I still want to see your explanation in the space provided underneath the question. Okay, so in the box, you just put true or false, but then in the space provided, put the other space provided, put your explanation. And most of the credit on that kind of question, when I'm grading it, goes for the explanation, not for what's in the box, right? So if you luck your way into the answer true or false, you might get a point or two, but you won't get full credit for that piece of the problem. And when I'm making up a true-false question, they may include a short calculation that you would then use to say whether something was true or false, okay? And one of the reasons why I'm doing this is that, as you can see in the topics that we've been covering lately, we're getting into more kind of big analyses where, you know, the results of at the end of your analysis may be very dependent on the things you got at the beginning of the analysis. And so I'm trying to make sure that I'm not going to penalize you for making a small mistake at the beginning and therefore not being able to proceed all the way to the end. And one way to do that is to break it up using this kind of true false or small short answer kind of problem. Yeah, I just wanted to clarify that because I guess aside from, there were a few, like in the Python example, the Python question on quiz 2, there was a question about whether or not the DDOF parameter, the delta degrees of freedom parameter, was correct as the input to np.var. That's an example of kind of a true-false type problem that we've had so far. But there will be more of those. So another clarification on quiz 4, this came up, some questions some of you had at office hours or when talking to me, is about how to compute the t-distribution if you don't have Python, right? Because you're not going to have Python on this quiz, but hypothesis testing using the t-distribution is an important piece of what we've learned since our last quiz. And so I'll give you a t-test table as part of your equation sheet, and it basically lets you look up results that you would otherwise have computed with the t.ppf function. And so there's an example here to relate the code, which we looked at in class, to or that you've been using in your homework, to the t-test table. And so you should take a look at this to make sure you understand how to use the table, because that's where you're going to be getting your numbers from. But we can just we'll look through this right now. So let's say we're doing a two-sided t-test with alpha is equal to 0.05 and 10 degrees of freedom. So the way I would do this in Python is with the t.ppf or the stats.t.ppf function. And this is the way we typically have written that out, right, in class. So we're running t.ppf of 1 minus 0.5 times alpha with a specified number of degrees of freedom. And remember, this ppf is basically the inverse of the CDF. So it's asking us, it's answering the question of, for a given area in the CDF, in the cumulative density function, and a given shape of the t-distribution, right, what is the value of the t-statistic that gives us this area? Yeah. You would get a negative number. So if you didn't do the 1 minus, you would just get a negative number here. Yeah, that's correct. So yeah, and we do this 1 minus, so we're getting something from the right-hand side where we have positive t-statistic. That's correct. And note that in here, I'm using a two-sided t-test. So I have this 0.5 times alpha, right? If I want to do this at a significance level of 0.05, I have to look for the value of the t-statistic at which I would have half of that significance level in the area outside the curve. So I have that 0.5 times alpha. So when we're doing this in the from a t-table, what we're going to have to do then is, first of all, figure out what is the alpha value that we're going to be looking up within the t-table that we're going to use to look up the value of the t-statistic from the t-table. In this case, it's that 0.5 times alpha, the same thing that's in our code here. So we're going to be looking up, we're going to be looking for a t-statistic that corresponds to this number of 0.025. So this is the result that we get from that t.ppf. We get 2.228. Let's say now, so we have this alpha that we're going to use in the t-table of 0.025, and we know the number of degrees of freedom that says the shape of the t-distribution is 10, right? Again, those are the inputs to our t.ppf function. And so this is what the t-table looks like. It gives us, for a given value, which it refers to the area underneath the right-hand side tail of the t-distribution. So for a specified area, that's shown up here on the top, and a specified number of degrees of freedom, that's what's shown down here on the left-hand side. Right, so that specifies the shape of the curve. It gives us the critical value, or that t-star value, that we would normally find from t.ppf using Python. And so in this example, we had we were going to look this up based on an alpha value of 0.025 with the degrees of freedom of 10. So we ended up with 2.228, the same thing that we got from the Python code. Okay. So this is the way things were done in the land times before having this kind of code at your fingertips. But this is more or less just giving you, again, exactly what the kind of result that we have from Python. Okay. So I'll give you a version of this on your equation sheet, along with a little bit of code, something like this, that's going to tell you about how this relates to the code and the way you're used to seeing it. Okay. So whenever you would ordinarily solve a problem by writing this line of code, instead you'll be looking it up in this kind of distribution. Okay. All right. Any questions on that? Okay. So expect to see that as well. All right. Some other notes I just wanted to, and clarifications I just wanted to go over that came from conversations with some of you over the past couple of days. One thing is that we have many different ways. We've talked about many different ways of computing 95% confidence intervals. So one of maybe the more difficult things to keep track of on the next quiz, and one of the things to make sure to review before the next quiz, is just like, under what circumstances do you use what method to compute a 95% confidence interval? So similar to in previous quizzes, I told you one of the key things that you might get confused on, and that you should definitely review, is knowing when to use which distribution. Right, that was on a previous quiz. For the material that we've covered more recently, we've discussed a number of different ways of estimating 95% confidence intervals. Right, so we've talked about propagation of uncertainty, which we'll talk about again in just a second. We had a simplified propagation of uncertainty equation for a linear expression, but for a nonlinear expression, we had, the partial derivative way of propagating uncertainty, 95% confidence intervals. We looked at 95% confidence intervals when we have just a single value for the mean. We have 95% confidence intervals on our linear regressions. We had 95% confidence intervals when we have a paired t-test or a paired sample t-test and so on. So we've looked at many different ways of computing 95% confidence intervals depending upon exactly what situation we have. And so in some sense, one of the key things that I'm going to be quizzing you on is knowing when to use which one of those expressions or which one of those methods. Okay, so that's something to get straight as you're studying. Another thing is to watch out for propagation of uncertainty. And when we have so we went over a general expression to take a functional form that relates some output random variable to some input random variables. And that general form includes partial derivatives, right? So we need to use partial derivatives in order to find the sensitivity of our of error in our output value to error in our input values. That's the method you should be using to propagate uncertainty. Okay, so I've talked with some people who are using who are doing things like taking the min or max of the range of the various input values and plugging them into the original formula in order to propagate uncertainty. In some cases, it gets you the exact answer that you would get with the partial derivative method. In other cases, it's wildly incorrect. And so what I'm looking for you to do here is to use this propagation of uncertainty based on the partial derivatives, the method that we went over in class. Okay, same goes on your homework, homework 7. All right, any questions on any of this? Okay. So for today, we're going to be talking about nonlinear regression or curve fitting. I'll say that this is going to be much more of a practical description of nonlinear analysis, of nonlinear regression, where unlike, so in linear regression, we showed a set of equations that we can use to basically do a linear regression by hand. The way that we'll look at nonlinear regression is more or less just using code, right? So basically how we would do this using Python code. So it's the type of thing that we wouldn't generally do by hand. But we'll look at some examples of how we can apply and in what cases we might apply nonlinear regression, because it is an important extension of regression. And we'll also look at how we can perform nonlinear regression, not only when we have a functional form relating an output to an input, right? So y is a function of x, but also when we have a differential equation that relates an output to some inputs or to an input. We'll look at how we can perform nonlinear regression for that kind of situation as well. So we're going to start with an example. So we're going to say, let's say we begin with some function. So we have y is equal to ax over b plus x. And the goal, remember when we were doing linear regression, right? Let's say we're saying fitting to y is equal to mx plus b, right? Using linear regression. The goal of that regression was to say, based on the data that we have for y as a function of x, we wanted to extract the parameters, m, the slope, and b, the intercept, that best fit that data, right? That's kind of what we did in linear regression. In nonlinear regression, what we're saying is that we have some function relating, in this case, y to x, that's nonlinear, right? This is not a straight line, but it has unknown parameters. And so what we're going to do is we're going to try to take data for y and x and figure out what values of those parameters, in this case, a and b, what are the values of those parameters that best fit or minimize the error between our model and the actual data. And so that's the goal of nonlinear regression. So in this case, we're given that this is the function that we think might fit this data. Our data is given here, x and y, right, defined as these two arrays. And so what we do is we have to then define a function that we want to use to fit our data. We need to define this using a function definition within Python, right? So up till now, we've kind of been optionally using function definitions in Python, for example, to show that we can compute summary statistics, right? We wrote our own function, lecture 1 or 2, we had our own function in here in the notes to compute summary statistics on some set of data. But you could just as easily have done that without the function definition piece, right? For this nonlinear regression, we're going to need to define a function, which basically says for our given input to this function, or given input x and parameter values a and b, right? Remember, these are the things that we're trying to find in our nonlinear regression. But for a given set of parameter values a and b, what is the output, right? So in this case, it's simply our equation up above, translated into Python code. We're saying g is equal to a times x over b plus x. And then our function returns the value of g, okay? So we need to define this function in order to do nonlinear regression. In this case, we're going to use a toolbox for this. So another thing that we need to do, and this is a little bit distinct from what we saw in the linear regression case, is that we also have to give an initial guess. So we also have to say, give some value of what we think A and B might be in this case, or whatever our parameters are. We need to have some guess as to what we think those parameters might be. And so in this case, we're going to use initial guesses of 1 and 0.1, maybe based on something else we know about the function or the data or what it represents. And then we're using this curve fit function, which, just double check where we imported this, which we imported from scipy.optimize, right? So we imported this curve fit function. So we're going to compute the curve fit. Our inputs are function 1, our data for x, our data for y, and our initial guess. And we get these outputs, which are the parameters and this covariance matrix, which we'll look at how we can use that. But this first output here of that curve fit function are the parameters that best fit our data, right? So these parameters, these are the values of A and B. Here I'm displaying them without regard to significant digits as about 1.3 and about 0.03. So those are the values that best fit our data, but this covariance matrix, the other output of this curve fit function, is what we can actually use to tell us about uncertainty in the parameter values, right? And this is going to tell us something about how good our fit is, and about what we know about those parameter values. And so if we have those parameter values, so we're going to take the diagonal of that matrix. These are the values we get out of that matrix. And we're going to be then computing a 95% confidence interval and using a t-test. And remember, if we're computing 95% confidence interval using a t-test, we have to answer two things. First is, what value of the t-statistic do we use? And the second is, what value of standard error do we have? Yeah, that's a great question. Yeah, so the question is, do the parameter values depend on our initial guess? So they shouldn't, but they will. So if you make it, depending on the function and depending on the function, it may be very sensitive to those initial values. So some functions may not depend very much at all on the initial values. Other functions may depend very strongly on the initial values. I'll leave that as a topic for numerical methods, which I'll take in the spring, and you'll talk a lot about this kind of thing. But yeah, it can, and at times the output can depend very strongly on those initial values. What can happen is that you can get stuck in what we would think of as like a local maxima, right? Where you end up with like some local optimum, right? Because you've chosen parameter values. Let's say instead of 1 and 0.01 or whatever we said here, you started with, 100 and 1,000, right? You might find a fit to some set of values that are not these, that maybe don't fit as well as these do, right? But but still fit better than anything that's kind of nearby. And that's definitely a risk with this. And it's one of the tricks of doing this kind of nonlinear optimization. But again, it requires a little bit more of a study of the numerics to get there. Yeah. Was there another question? Or are you saving it for Dr. Saad?
My question.
Maybe, not always, but maybe. So in practice, kind of glossed over here in this example, but like if we have this function, we probably have some idea of what those parameters, right? This, as engineers, we're typically trying to fit data that relates something real to something else real, right? Using a model that represents something real. So, you know, we may have some idea of what these parameters are, even if we don't know exactly what it is, right? If this might be a rate constant, right? And like something with units of concentration, like Michaelis, like let's say we're doing something with Michaelis-Menten or something. We might have some idea, even if we don't know exactly what the value is, because there's no published data on it. We can probably make a pretty good guess. And so you'd want to start with what that pretty good guess is. An alternative is if you know the data, you know, it might be that like one of these values, like this value B, you might guess should be of the same order of magnitude as this value X. So you might just say, as an initial guess, I'm going to say B, my initial guess for B is the average of X, right? So you might do it based on your data as well. But again, it gets a little more advanced. Yeah. Any other follow-up or? Okay. But yeah, that's kind of the dark arts of nonlinear regression. That's how you fit your initial values. Yeah, going in with no knowledge is more likely to result in an incorrect final answer. Yeah, so generally you want to have some idea of what you're looking for. Yeah, and that can come from the data itself. It can come from previous literature. You know, it can come from sort of analogous things, right? You're trying to analyze some process. You have data from a new process, and so you don't know what A and B are, but you have data from a previous process that, you know, you might start with those values instead. Yeah, okay. And again, as engineers, we don't need to solve that problem in general. We just need to solve it for a specific set of conditions that generally describe something physical. Okay, so we're going to be computing a 95% confidence interval from the data that's in that covariance matrix. And in this case, so again, then the problem, and we're going to do this using a t-test. And so the question is, what value of the t-statistic, and what do I use for standard error, right? And so as far as the t-statistic, we need to know the significance level. In this case, it's a two-tailed t-test. And so we're trying to do this at a significance level of 0.05. And so we're going to be using this, we're going to be doing t.ppf with this 0.5 times alpha. So again, if we were doing this in the table, the lookup value that we'd be using across the top of that table would be 0.025 or half of alpha, right? Because we're using this, we're doing a double-tailed t-test. In this case, the number of degrees of freedom is not the number of measurements minus 1. It's actually the number of measurements minus the number of parameters. Okay. So if we had a 5-parameter model, right, we have fewer degrees of freedom. So our degrees of freedom now is n minus p. In this case, we had 2 parameters, right, a and b. We had however many data points we had. And so that sets the degrees of freedom, which is how we find our t statistic. And then our standard error that we're going to use is actually just the square root of those covariance values. MP dot square root of the diagonal of that covariance matrix. So here we're outputting what we're using for that standard error. And so then our margin of error is then just our t-value times those standard errors. So these are what we get for our margin of error. And now this code down here is then going to basically export or display and properly format our results, or display and format our results. So we're going to say that for the first parameter, which is our A in this case, we had a parameter of 1.33, and it's plus or minus 0.03. Yeah, go ahead. What's that? PCOV. So PCOV is it's the covariance matrix. So it tells something about how much error there is in your output based on changing those parameter values, or like how different your fit is, or how your goodness of fit changes as you change your parameter values, is kind of a working definition of what's in that covariance matrix. So the diagonal then is telling us specifically just for varying A or B, how much that changes. So that's why we're taking the diagonal here. Yeah, and the first value on the diagonal tells us about the first parameter, and the second value on the diagonal tells us about the second parameter. Yeah. So in this case, then we have 1.33 plus or minus 0.03, which is probably how I would format it in terms of significant digits. And for the second parameter, we had about 0.003. Sorry, we had 0.026 plus or minus 0.003 is what we have for our output. So this gives us a sense that our parameter values that we estimated are actually, we know pretty well, right, from this data set, because we have pretty tight 95% confidence intervals on those values, right? So we can say that we have a pretty good sense that this value is 1.33 and probably not 1.4, right? Because we have such tight confidence intervals here. In fact, I'm going to change this. Yeah, for both of these, we're going to display these as with a more appropriate number of, sorry. It's running it based on a different calculation here. Okay. So we'll display this using a more appropriate number of significant digits as this. At least this is definitely an appropriate number of significant digits for the second parameter, and you might use one fewer significant digit to express the first one. So this is one way then of evaluating our goodness of fit, is just how tight are the confidence intervals that we would compute on the parameter values. And again, we get that from that covariance matrix, which tells us something about basically how good the fit is for each of those parameter values, or how well we know those parameter values. We can also obviously plot the data, which is we probably should have started with, but here we plot the data. Y as a function of X is shown as our symbols, and our fit is shown as that line. Somebody who does experimental work, like if you ever get a fit like this is fantastic. This almost never happens. But here we have, in fact, a very, very good fit between the model and the data. Just as a note, for as you're working through labs, when you get into junior labs and your senior project, in general, when we're displaying data and a model, this is often the format that we use, where we use symbols to represent the data and a solid line to represent the model. So that's just general formatting. So you notice here that I'm not displaying it with like connecting lines in between the data set, because those are kind of distracting. I'm just displaying the data points themselves, and then the model that goes through those, or the model to that I think describes those data points. Okay, so that's kind of like a working example of how we do nonlinear regression. We have another example here, which we'll go through a little bit more quickly, because I want to talk about what exactly we're doing in nonlinear regression, and then give an example of how we can do this for a differential equation, for a model that's based on differential equation instead of a closed form solution. But so this is another example where we're going to have some function. We're going to get some output. In this case, we're returning it as this value of g. And it's a function of x with parameter values, in this case, a, b, and c. Right, so we have, this is what the function that we're trying to fit. And So the definition of the function we're trying to fit, so it's a times the exponential of minus bx plus c, right? So it's an exponential function with a constant. In this case, as an example, we're basically creating fake data. We're going to add some noise to it, and then we're going to ask how well the fitting parameter recovers, the fitting process recovers those parameters. So we're going to create some data that we store in y with parameter values of 2.5, 1.3, and 0.5. And we add some noise to that data. And we're going to add that noise with some prefactor to scale that noise to the data. So we're going to get some output data set y that generally follows this function with these parameter values a, b, and c, but not exactly because we added some noise. And then we'll see how well we can recover those original parameter values using our nonlinear fitting, right? So this is just kind of a test of our fit. So here we actually do the fitting, where we have some initial guesses which are close but not exactly what we know the parameter values are. So we could use this, for example, to test, like if we put in 100 here instead of 1, like how close do we actually get to the fit? We'll try that after we look at the output. Then again, we're computing the confidence intervals. We're going to end up computing confidence intervals on our output results, which are then going to be displayed down here, and then we'll plot the results. So in this case, we end up with for our first parameter, we know the input was 2.5. We end up with an output of 2.4 plus or minus 0.6. So that's definitely within range. This one, I believe, was 1.3. We ended up with 1.2 plus or minus 0.8. So again, it's within range. And our third parameter looks reasonable with what we knew it should be, about 0.5. This was what our data actually looked like. So the sort of synthetic data that we made is shown again as these closed symbols. And we can see that it generally follows this kind of exponential decay. We added in some noise so we could see how well the fitting function performs. And the fit did a reasonable job of recovering what we had. So again, just another example of how we can actually compute the fit for the data. I just want to see, I haven't done this before on this data set, but we'll see what happens if we put in, I don't know, an initial value of like 100 and see what happens. Yeah, and so you saw that we ended up with something that is just a complete mess, right? So we have a fit that really doesn't match the data whatsoever. And we in fact got an error, right? Because something telling us that something went wrong. It doesn't tell us exactly what went wrong, but something went wrong. In this case, it had to do with our initial values. But if we use, let's say 2, we should hopefully recover the right thing. Yeah, so we use the value of 2 and we end up getting someplace that's actually pretty close. All right, so a little background, and as deep as we're going to go on the theory of nonlinear regression is just a description of what it is that we're trying to do here. And this is, again, very much analogous to what we did in linear regression, but now it's using methods that are applied to a nonlinear function. What we're actually doing in this optimize curve fit function is we're using this Levenberg-Marquette algorithm so again, we're going to say that we have some set of data points, x1 through xn, with corresponding function values y1 through yn. And we know that we suspect that there's some function relating x to y with some unknown set of parameter values. Right, so we're describing it here as a vector of parameter values p, but this is just a list of a, b, c, whatever our parameter values are. So we're trying to find that parameter vector, right? The list of those parameter values. And what we're actually minimizing here is the sum of squared errors. So just like we were doing in linear regression, we're minimizing the sum of squared errors. A big difference is that because this is nonlinear regression, we're prone to things like having these local maxima. So we have dependence on our initial conditions. We don't have a direct solution for exactly what these things are, right, as a function of our data, like we did in the linear regression case. So this is squarely now falling in the realm of numerical methods, like how it works. It's squarely falling in the realm of numerical methods. It is something you'll talk about more in the spring. But but we are more or less trying to minimize the sum of squares, just like we did in linear regression. All right, any questions on this so far? This is really a lot more of a practical introduction to nonlinear regression. So one of the features of nonlinear regression. So if you remember up at the start of this lecture, I said that we had to define a function which relates our input, right, our x, to the output in terms of some number of parameters. And if we have a closed form solution, right, so if we have an equation that directly relates those things together, our function basically just computes those things. But there's really no reason that it has to be that way. We don't have to have a closed form solution. We don't have to be able to express it as just a single equation. We can do nonlinear curve fitting when we have a more complex underlying way of computing the relationship between our y and our x. And so one way of implementing this is using, or one way of using nonlinear curve fitting is when we have a set of differential equations that describe the relationship between y and x, right? So we don't have, even when we don't have a single final equation. And so we'll look at an example using, so we'll start here actually by just discussing how we can then fit, or just a reminder of how we can do numerical integration of, or maybe an introduction to how we can do numerical integration from a differential equation or set of differential equations. And then what we'll see is that we can then take that and put that as the input or as a function that we use in our nonlinear regression, and then use that to estimate parameter values. And this is often something that this is something that's important in engineering, because we often know a differential equation that describes a process. Like we might know differential equations describing a chemical process, right? We know differential equations relating the concentration of some output to concentration of some input. But we might not be able to write down one equation that just describes the concentration of that output as a function of the input. We might only be able to express it as a set of differential equations. So this is an important thing to go over in the context of engineering. So the function we fit can be in the form of differential equation with unknown parameters that we numerically integrate to recover the parameters that describe that differential equation. So we're going to start with an example of transmission of disease. Something called the SIR model has to do with, and we'll see what the different parameters, SIR, are different parameters that are in the model. So this is a differential equation model. The SIR model is a differential equation model for the spread of disease. And it starts by assuming, let's say, during the period that we're looking at our data over, let's assume that there's no deaths. So we're not losing any people out of the population due to death from the disease. And so what we say is that total number of people in the population, right, so N is the whole population. It's composed of people who are susceptible to the disease, people who are infected with the disease, or people who are recovered from the disease. Right, so we're going to say that everyone within the population is, has one of these three states. Right, there are modifications to this model that would account for births and deaths and everything else, but let's just start there. So then if we have a number of contacts per unit time for each person as C, and I over N of those contacts will be with an infected individual just by random chance. R is the fraction of contacts that result in infection. So it's something like the infectious rate of the disease. And K is the recovery rate. So 1 over K is the average length of time someone's infected. Not dwelling too much on the models of this parameter because it's not a class on modeling disease, but rather a class on how we can use this kind of thing. But from that, we can then develop an expression for the rate of change as of S of the susceptible population as minus SCR times I over N. So it basically has, so we end up with, we're going to group those things together into a single parameter beta that we might want to estimate using our nonlinear regression. We do the same thing for the rate of change of the infected people by more or less tracking inflows, people who become infected minus the people who recover. And recovered is, again, we can track basically where the number of people who are recovered is just the difference between the total number of people in the population and the people who are susceptible or infected. So one thing that's a little distinct when we have a differential equation is that we also have initial conditions, right? So we're also going to have to set initial conditions. In this case, we'll say initial conditions are SI, RI, and II. And we're going to say the number of people in the population N is constant. So we can then write an expression for the initial growth rate of the infected population. So assuming that we start out with a small proportion of the population that's infected, again, not going through the derivation, we end up with this differential equation saying di dt as a function of our parameters. And the goal, more or less, of vaccination. So this bit tells us that we need to have this parameter here be greater than 1 for the epidemic to get started or to take off, for this thing to grow. If this parameter is less than 1, then the number of infected will decrease. So a note is vaccination is more or less trying to decrease this parameter here to make this whole term less than 1 so that the infection rate doesn't take off. From this expression, we can do things like, you may have seen this as in vaccination discussions, right? Like, what is the fraction of the population that needs to receive a vaccine in order to prevent spread of a disease? It comes from models like this, right? Our estimate of that more or less comes from a model like this, where we say, like, what is the, we can use a model like this to figure out the fraction of the population that needs to be vaccinated to ensure that the rate of growth of infected population is less than 1, or that that the disease is dying out. So for H1N1, based on the parameters that we would estimate for growth of that disease, we'd estimate you only need to vaccinate about 29% of the population. So one thing that's to keep in mind when we're doing this kind of a curve fit, it's often useful to scale your results. So this also helps with the question of how do you choose your initial parameters, right? How do you choose your initial guesses? If you can somehow scale your results so that everything is between 0 and 1, or everything is within, or all your numbers are of comparable size, then it tends to be better behaved numerically. And again, it's something I'll talk about in numerical methods. So in this case, we're going to scale everything. We know that we have a natural scale built in, which is the number of people in the population. And so then we'll look at kind of relative numbers of people that are in each one of these groups, the S, I, and the R group. In that case, we can recast this expression in terms of scaled variables, which are here going to be lowercase. ds dt, for example, is minus b times s times I. And this is our expression then for rate of change of I. Again, not going through this, not dwelling on it too much. But again, and then we have our initial conditions here. But more or less by rescaling this, it's often the case that we'll get better performance of, for example, our nonlinear curve fitting or nonlinear regression type procedure. So we can then, but now if we have a process, right? So in this case, it's a process of infection from some disease that we've now described in terms of a set of differential equations. We can numerically integrate in order to find, like, for example, what are the proportions of the population within each one of these bins as a function of time, right? So even though we don't have what we would call a closed form expression or a single equation or set of equations that directly relates these S, I, and R proportions to time, right? We're not going to say, like, we don't have S, like the susceptible population, as a function of time. We have a set of differential equations that describes how things change. We can now numerically integrate that set of differential equations to solve for what those things look like as a function of times. So, for example, if we take the susceptible population here as 8 million or 7.9 million, let's say we have 10 initial infections and initially 0 people recovered, right? So we're trying to model the early stages of some kind of pandemic. We can then recast our numbers in terms of those scaled parameters, lowercase si and r, based on basically a total of 7.9 million people in the population. And then based on some parameter values, we can say, in this case, we'll say k is 1/3 and b is 0.6. We can then take those parameter values and define, this is really the key piece that we've been building to, we can then define a function. Well, first we start by defining a function that computes the derivative of each one of those values. The derivative or the rate of change of, in this case, our s, I, and r for each one of the variables. And then we can find those variables as a function of time using this solver, right? Using this numerical solver, which basically numerically integrates these our parameters, or sorry, our variables, in this case, si and r, over some given time span, right, that we have. Right, so we can use this solve IVP to, and even though we don't have a single equation relating these parameters or saying what these parameter values are as a function of time, we can figure out what those parameters are as a function of time using numerical integration and then plot them, right? So in this case, we're plotting those values for s, I, and r as a function of time. And we're seeing here that we have, we're predicting in this case that this particular, right, for this particular parameter values, we get a peak of around 50 days or something in terms of number of infected people in the population. We could use this to compare to some data. So in this case, we're comparing it to data for a flu pandemic in New York City, where this is the number of excess deaths that occurred within the city. We would expect that to be proportional to the number that were infected. In this example, we're just going to look at the fact that plot has roughly the same shape and peak time as what we would expect based on those parameter values. We could potentially go back in and try to solve this using nonlinear curve fitting, although that's not actually what's shown here. So the key takeaway from this example is that even though we didn't have we would say a closed form expression saying, for example, the number of people that were infected within a population as a function of time, as long as we could write a system of differential equations that described that, we can still generate this kind of a plot. And then we can still use this kind of an output as the input to our nonlinear curve fitting to then estimate parameter values. Okay, and that's what's shown here. So if we have, so again, by example, so if we have, we'll use something simpler here though, right, instead of the disease model. So we'll say that we think the solution dy dt equals ky describes some data that we have, and we want to fit an ODE to the data to determine k. Now this is a case where we could solve this directly, right? But it may not always be the case that we can solve this differential equation directly. Just a note is that we're using solve IVP because this ODE int, which is actually shown if you go to this website, is deprecated, meaning it's no longer supported within Python. So we're using the solve IVP, which is what we've been using so far. So again, we're going to have the same kind of setup that we had previously, right? So we have data to be fit, in this case, in terms of some output y as a function of some input t. Okay, so this is the setup. This is what our data is. Again, we're describing a fit function, right? So one of the things we need for our nonlinear curve fitting is a function that we're actually going to fit to that data. What's different here is that fit function is now in terms of this ODE solution, right? So we're actually using the solve IVP, or we're using the ODE solver, the ordinary differential equation solver, within the fit function. But we still are giving our output t as a function of the input parameter k. Sorry, it's still giving our output, our solution to that. It's still giving our solution or our value y as a function of our input, in this case time, and the parameter, which we only have one parameter here, which is k. So again, we have to make an initial guess, right? So from here, it's all the same as what we had for nonlinear curve fitting when we knew what the functional form was, right? So we have our initial guess. We have our, we're going to compute our parameter fit and the covariance, which we can use to estimate the 95% confidence intervals. We're using that curve fit function. But now our fit function, right? The big difference is that our fit function does this solution. And so nested within our fit function, another thing to point out, is nested within our function is a definition of that differential equation. When we do this, in this case, here's our data, and it's shown in red, and our fit line is shown in blue, right? So we've done, again, we have a great fit between our data and our result. We estimated what our k value is, right? We can output what our estimated k value is. In this case, it's minus 2.524. We have this decaying exponential process. And just as we did before, we can now estimate 95% confidence intervals on this k value. Even though, again, it's nested within a differential equation, we can still estimate 95% confidence intervals and fit to what, and estimate what this k value is from real data, okay? I know we've traveled a long way to get to the conclusion that we can do this when we have a differential equation as well. But that's more or less what the last piece of this lecture was about. Any questions on that? I know we went through a lot of Python code to get here. Okay. All right, so that's where we're going to end the lecture for today. I know there have been some questions on the homework. I'll be happy to talk about those kinds of things if you have that now. But as a reminder, again, we have that quiz coming up on Monday. I'll be getting that equation sheet to you as soon as I can by the end of this week. All right, thanks.